like before we get started, so I mean, power has become like very critical, especially for the telco operators, and we see a lot of concerns around basically efficiency in terms of power management and power efficiency and better performance per watt, things like that. So in that regard, basically what we are hearing from various customers is solutions which are generic across platforms, so that they can build a solution which can be scale across different platforms, things like that. So in that regard, basically we started this journey around 2 years back, enabling the various capabilities of AMD APIC servers in the DPDK space. So one of the things where we see require a lot more, I mean we see some challenges or some inefficiencies in terms of adapting basically specific drivers into the DPDK ecosystem. And we felt something is can be done better, basically it becomes easier, and also we see as we go forward a lot more players are coming into the space and it becomes easier for them, and what can be done better to make it more efficient and easy to plug in kind of thing. So before we get started, let me just introduce what is DPDK Power Library about. So it's basically hey, we talk about DPDK as it gives better performance through poll mode, things like that. What it means is the moment when cores are busy polling, it's going to consume more power. So it's trade-off between power versus performance. But as we go forward, we wanted to balance both of them, given that power is getting critical as well. So DPDK has a power library basically to optimize power savings, on for things that are managed by the DPDK, cores that are being managed by the DPDK, things like that. And how it does this is it provides a frequency management infrastructure for both core and uncore. And also there is infrastructure basically to put some of the cores into the idle state, for cores that are idle and not processing anything. And along with that, there are a set of adaptive algorithms. Again, these are custom specific that can be adapted as well, to new platforms and new requirements and to meet new KPIs, things like that. So there are a set of adaptive algorithms which does this live monitoring, and based on that, select an optimal frequency state, or you can use some kind of heuristic mechanisms to determine whether the core is idle or not, and put a core into idle state. So the second, there are certain Uncore APIs. Again, this is something that we'll touch base on, how we can extend the scope of it, because there are a lot more things that can be possible as well. So in the today we are going to talk about refactoring the power library in the first part. So how we can modify the existing implementation to make it more plug and play kind of approach. The second part is about the new vendor agnostic Uncore APIs, to have a common solution across different vendors. So what we have in the current power library implementation is something like this. So basically the existing power library is built on top of the Linux operating infrastructure, OSPM. So we have basically different kernel drivers basically for different frequency management things, like ACPI, or in specific PCI drivers for different vendors. And there are also certain Uncore drivers basically for Uncore frequency scaling and things like that. So when the power library was introduced, so basically there were a set of components being introduced to the library space. Again, each is coupled to a specific kernel driver. And there is a generic power core library which is on top of it. So what application sees is the power library, core library, which links with the different specific implementations under the hood. It is good. It's basically working fine. So what application has to do is, when you build the DPDK, so you'll have a power library with all these components coupled together. So when application builds this, links this power library to make use of the power capabilities, it will become a huge thing. And application has to just link the library with all the different components in place. And then you can, at the application level, you can choose what operating environment you are on, and based on that you can set a specific environment, which is going to basically enable the power library to identify the respective driver hooks, and call those hooks as needed when you request for any frequency management. So this is good, but like, what we have, like, what it means, like, what are the challenges that we might encounter. So the first thing is basically, so when you build the library, like, you'll see all these components are like, bundled together as a single library. And when you just link your application, your application will be linked with all the components together. So when you see it, like, whether it is relevant or relevant, you see all those components being there, like, it becomes a big component, which may not be required basically, like, if you are not going to operate on those specific environments. And looking at the build infrastructure, things like that, yeah. So if you wanted to make disable certain things, so you need to make changes to the build infrastructure to explicitly remove it. Again, you have to do patching, things like that. But that is something like, what if you, that is one problem. Second problem is like you might be switching between the, like, between different p-state drivers within the same platform itself. So that is also like, I mean, every time when the kernel switches to a different frequency driver, like, you have to rebuild the application with a different patching, things like that, which is not going to be efficient. So what we thought is like, there are certain things that, like, what is the motivation for us to think about, like, making these cleanups and things like that, is basically, so as we add more libraries or as we add more like, frequency management capabilities and new drivers into this, so the library is going to like, blow it up. What it means is it's going to increase the code size. It might affect the performance. The second thing is every time when we wanted to add a new library, you have to basically add that additional component within the library space, and you have to modify the core library as well to enable that new components, right? Which is a double effort basically. So why, I mean, what it means is you would have to test the core library to make sure you're not breaking anything, and along with like the new driver that you're introducing. The second part is like, this is good, like, if you have limited set of drivers, but like, as we add more and more capabilities, so it's going to blow it up exponentially. So which is not a scalable thing. And the other part is like, if you look at the current library, there is like, you would see that, okay, there is a specific component, there is a generic component. The generic components calls like various hooks of the specific components here and there. So I mean, there's like basically there is something that like we can just rework on it to improve the code clarity, things like that, and modularity aspects. And again, like, we want also like, for example, you might have a specific frequency driver which has additional dependencies. So like when you try to build it, like, basically you would have to resolve those dependencies for your library to build successfully, but that dependence may not be relevant for your things. So like, if you wanted to remove the sort of cyclic dependencies, things like that, which are not relevant for you, so you can simplify things better. So that's one of the reasons for this refactoring thought process behind. So what we took the approach, right? So basically what we thought is like, we'll go with a phased approach. So the first thing towards that is what we did was we looked at the basically Uncore part, which has some vendor specifics or vendor locking. So we tried to make it generic. That we did in 2311. So we added a generic Uncore APIs. I mean, basically in line with the core Power Library APIs. And then we started this. So basically, we proposed an RFC basically to refactor the existing implementation, bring in new sort of power drivers under the drivers hierarchy. So, and basically make the library as thin as possible, so that like, these drivers can just plug it into the library and then like, enable the capabilities, things like that. And the other thing that we are also working on in parallel is basically propose some sort of vendor agnostic Uncore APIs to enable more and more capabilities of the Uncore components in the platform. And like, in the process, we are also supporting the, basically AMD Uncore driver support, I mean, for Uncore implementation as well. And the other thing is like, I mean, as we speak about the code cleanup things, right? So one of the things that we see is, hey, like, why you wanted to set basically the Power Library is coupled with the Linux operating system, which is currently supported, which is the only one that is supported. So Linux is not supporting more than one operating environment at any given point of time. Why application have to be agnostic about, I mean, have to be specific about the operating environment when it has no control on the operating system. So this power environment set APIs doesn't look relevant in that regard. Rather, like, what we would be looking at more is like an auto detection capabilities, which I think should be the default behavior. So in that regard, basically, I think what we are also planning to propose is deprecate these APIs as well. Again, like, we wanted the community to hear feedback from the community about these changes. So the new implementation is something that like we submit to the RFC, and again, like, we got acceptance from the community, and we are going to push we are targeting these patches for this 24.11 release. So the new implementation will look something like this. So where you have basically kernel drivers and you have user space drivers. The user space drivers are going to be coupled with the kernel drivers again. But like, at the library level, it will be very thin. Like, you have core library, you have Uncore, both are part of the power library. So the core library, like, there are a new set of operations being defined, like, for various frequency management, things like that. So there are new structures being introduced, like, for core power management, Uncore power management. And each driver that has been enabled on the system, like, when the driver is loaded, it registers itself with the power library. And then, like, application, for the time being, like, you can select explicitly what operating environment you are on, or you can let the auto detection to detect the operating environment and then hook the respective frequency management operations up respectively. So what it brings, right, like what these changes are going to bring is, like, so you can explicitly disable these, like, drivers which are not relevant for your platform. Something like, for example, if you are operating on AMD platforms, the only the supported power management drivers are going to be like ACPI, AMD P-State. I mean, if you wanted to be specific about a P-State, AMD P-State driver, which is enabled in the DPDK ecosystem. So you can explicitly enable only those drivers, and you can disable everything else, like using the standard Meson infrastructure. So, and with that, so what we see is, like, you can reduce the code sizing as well, because you are disabling a lot of things. And it is going to be like, reduce the additional dependence. For example, if you're talking about ARM CPPC driver, so which may or may not require additional dependency, those dependencies you don't have to worry about, because it's not going to be relevant for your specific implementation. So you can enable or disable specific drivers using the standard Meson, just like any other driver in the DPDK framework. So, okay, so let's assume that, like, let's say if I wanted to extend this, or if I wanted to plug in a new driver into this, so what it takes, like, what is really needed, right? You just have to define the various, like, you have to add the driver with various frequency management operations. I take an example as a dummy driver here. So this dummy driver, I'm going to define it with the various operations, and this is going to register with the power library. And then, like, I have to just enable that in the build infrastructure to make sure that the library is compiled. And I have to just register with the power library using this RT power register operations for various operations. And, like, my application can start using it now. This is all it takes. You do not have to make any changes to the library, things like that. So the next thing is, the second part is about the vendor agnostic Uncore APIs. So we talked about basically generic core and Uncore drivers. And, like, now I wanted to talk about, like, what are the specific changes or enhancements that we plan to propose and implement is about the Uncore part. So just to give a background about Uncore, again, like, this term is not very generic, at least, but at least what we felt is there are a lot of things in common, and it makes sense to have a generic or, like, common interfaces to make use of those commonalities among the vendors, across the different vendors. And like, all the specific things, like, abstracted at the driver level. That's, at least that's the high level thought process behind it. So from a, like, given, just if you look at the Uncore part, right? So you might have different platforms. I take platform A and B as a reference. In platform A, basically you have basically your LLC cache, you have basically your PCI subsystem, memory controller subsystem, and then we have various interconnects between the packages or within the package. Things like that. Again, the platform B has, like, for example, LLCs moved outside of this Uncore part. You have basically the other things after that. Again, there are some commonalities, say here, memory subsystem, PCI subsystem, things like that, and the interconnects. So most of the vendors support basically, like, both, like, again, frequency management in Uncore part. So whether it could be, whether it is like, different performance states of a specific component in terms of frequency or in terms of basically in terms of the width control, things like that. So those are something that can, I mean, like, at least those are something that can be exploited to get some additional savings. And one of the things, why this was now it is getting critical is, I mean, as we migrate, I mean, as we keep progressing across various generations, we start to see that the speeds are getting increased, whether it is PCI speeds or memory speeds and things like that. As a result of that, basically what it means is it's giving extra bandwidth with new generations, but at the same time it is drawing more power as well. So I mean, there are scenarios where, like, you might need extra bandwidth. At the same time, like, there are instances where you might not need that bandwidth. So you can fall back to a lower speed and you can save some power as well. So that was the thought behind this, at least why we are focusing more on Uncore part. So the challenges, right? So as I said, like, each vendor has their own power management technique when it comes to the Uncore power. Like, for example, different clock gating techniques or frequency management techniques, or whether it is dynamic voltage management technique and things like that. When you have so many, when you have basically when you are building a solution which can scale across different platforms, it becomes really challenging to have a power management solution which can scale across different platforms unless you have a standard sort of interfaces. So that was like the motivation behind it. So by having it, basically, like, you will you can save a lot of power in the Uncore part, like, I mean, when you have this right management techniques in place. And so with that, like, if you have a simplified interface, like, I mean, like with this, let's say when you have a simplified APIs, which does not really, like, worry about or how the implementation is going to be look, it becomes easier for the developers in terms of they'll see it as, like, top level view of, like, what are the different levels available at the Uncore level, and what level is more optimal for me to achieve a specific performance to meet the KPIs. So the Uncore software architecture with this refactor, post refactor will look something like this, where you have application and then there is a generic Uncore library. And then, like, under the hood, we have various user space drivers for different vendors, which are again coupled with the kernel. So again, like in core power management, so Uncore also, like, you can actually probe the platform, on which platform it is, and you can identify the, like, specific driver that is relevant for you. Like, something like, what we proposed is basically an auto detection capability. So which is going to look at the specific vendor it is operating at and then identify what is the relevant Uncore driver that can be activated. So some of the Uncore APIs that we propose, I mean, there are, again, like, just before, like, arriving at this, we explored a different solution, I mean, different approaches. Something like, can we abstract these things at the driver level and provide basically a generic, like, frequency level or performance level APIs. So each vendor can publish, like, can advertise the various performance levels that it can support. Like, what it means is highest performance level to the lowest performance level, and then, like, as you go up or as you go down, you'll start to see the lower bandwidth, things like that, but you'll save some power as well. So the driver can advertise itself with the different performance levels, and application can choose highest performance to the lowest performance, irrespective of what the platform is. And each driver can actually advertise different levels based on its capabilities. And like, the application can just probe it, and then, like, based on the available performance level, it can choose an optimal performance level as needed. So that is one of the things that we at least initially thought about. But subsequently, like, when we started to explore a little bit more, there is a combination problem, because different vendor will have a different way of looking at things. For example, let's say as you go from a high to low performance, what the again, the factor that we look at is the resource utilization part. So that resource utilization, when it comes to the, let's say, the telemetry aspects, it's not like, it becomes difficult to identify, like, to have a commonality among them. Like, as it will vary, like, for example, platform A will have component, some component which will give the highest power saving, but it might be different for a different platform. So that's when, like, we thought about those sort of approaches, but what we felt is, like, since there is a commonality among all the platforms, let's expose those commonalities, like, in the form of APIs. So that's where we come up with a sort of, again, like a micro APIs along with the, like, say, the existing APIs, which talks about various Uncore bus frequencies, things like that. So what we propose is basically a couple of APIs which will basically allow to set the interconnect bus widths, basically, and frequencies, things like that, along with the PCIe and various Uncore components. So with these APIs, basically, like how it is implemented is up to the driver. If the driver does not support a specific capability, it can just it can add a dummy hook, and what it means is applications will run seamlessly on those platforms as well. So with that, what it brings is basically a compatibility by moving away from the vendor locking, and applications it becomes easier for applications to develop solutions, power management solutions, and reduced complexity, things like that, and we can scale across different vendors, without having to really make any much adaptations to that specific platform. So with that, I conclude my presentation.
Any questions at all?
Yeah, I would like to say thank you to Shiva for taking this job of reworking power. I think you are quite courageous. In my opinion, you are just at the very beginning of your way. Very beginning. I think there is a big challenge around power with DPDK. That's our challenge of New Year's. That's what we have to do for sure. But you said you want to rework to make the code more proper. That's very good. I think we can discuss a lot of more things. For instance, about Uncore, I'm not sure there is a clear definition of what is Uncore, what it is today, what it will be tomorrow, and how we can design a good algorithm to get the best of Uncore with low power, depending on the hardware. We don't really know. If we reduce, do we get still a good performance? Maybe later there will be a critical component as part of Uncore, and it won't work anymore. Do you have a comment about that?
Yes, so that's one of the initial thought processes. It's the same thing. Different vendors have different ways of looking at different components. What is your best bang for buck in terms of where you can basically tune, where you can get the more savings, right? So that's where it was challenging basically to have a common API, generic API in terms of Uncore scaling up and down. So instead, what we felt is expose the capabilities in the APIs, and for example, there are certain things like Uncore bus, right? I mean, there is an Uncore bus which connects different components. You can scale up and scale down. This is going to be generic across different platforms. You have basically highest frequencies, which is going to consume more power, is going to give higher bandwidth. You have basically lower power states, basically, which is going to give you additional savings. So it is generic. Similarly, why can't you expose additional capabilities? For example, dynamic link management, right? Like you have an Uncore bus, or you have an Uncore, let's say, interconnects, which has some number of lanes, PCI and non-PCI kind of lanes. There are certain platforms which, for example, where we support, you can turn off some of the lanes when you have a low bandwidth scenario. For example, you can turn off from X16 to X8. You'll get power saving, but at a reduced bandwidth. So this is going to be generic again. That's where we wanted to expose that capability in the API.
Okay. Yeah, that's good that you bring the genericity on the table. That's also a big issue. First, do you know what is the performance power consumption difference between Linux and Windows?
Actually, so currently the power library is specific. I mean, it's at least it's only supported on Linux.
You got it. The difference is that we can use Power Library on Linux, so it's
Yes.
more better performing just
Yes.
for that.
Yeah, that's
No, but really, I think we need to do an effort on Windows. Is there anybody here who is already using DPDK on Windows? No, it was expected. But I think there is a future for DPDK on Windows. There is a big effort going on, and probably there will be more and more application for DPDK on Windows. So in my opinion, if we can plan for the Windows support, that's good as well. There are also more hardware to support. We can talk about RISC-V, etc. So it's a lot. But thank you for starting with this journey. Vipin.
Thanks, Thomas, for that comment. There is one small thing about Uncore. Please remember, now we have more cores. Okay, so if you can run more DPDK or user space application, and each core will be occupied by each application or process. But when it comes to Uncore, it is system level. There is no process 1, process 2, process 3. Everyone shares Uncore. So the problem what Shiva was trying to highlight everyone is, I being process 1, I can tell give me full speed. Shiva being process 2, he can request for lower request. Now which will the system or the driver choose or listen to? These are the problems we had when we were trying to introduce Uncore Max and Min. So that is why Shiva is telling us we want to break out from that. Instead, it should be like adaptive algorithm. In AMD EPIC SoC, we have algorithm or firmware which actually controls this. So all this power up, power down is actually a request you're placing. It can be either denied or satisfied. So that's what Shiva was trying to highlight there with Uncore. Thank you.
Any other questions at all? If not, then I think we're good. Thank you very much.